Hi everyone. In this video, I'm going to go through my attempt at solving the July James Louis puzzle. Um, and then I'm going to explain basically where I went wrong and how I failed to do so. And kind of take you through my thought process and what I was thinking when I was trying to solve it. So I recommend reading the actual question before this video so you get a better explanation of what I'm talking about. And so first thing I thought was obviously to calculate the loss of each car when it gets overtaken. And I basically found that the loss to be S divided by 2, where S is your speed. If you're in the slow lane, if you're below the threshold, and if you're in the fast lane, that you would lose, your loss would be S minus the threshold divided by 2. And then the second thing I realized is that that's just kind of complete nonsense, as seen in one of the examples in the question. And so I would later pretty easily find the losses to be this here by basically saying that if a car is traveling at a speed s and it has to slow down to a threshold where it can be 0 in this case, then that takes 2s minus a time, because you can only slow down at 1 mile per minute. And on average, you're losing s minus a over 2, like kind of speed, because that's your average, that you're below your max speed during your slowdown and speed up periods. And that's basically how I came up with this equation here. And then the second and more important thing, which I thought, oh my God, I'm so smart for coming up with this, was that faster cars are only ever going to catch up with your car from behind, and slower cars are only going to get caught by faster cars. And this is kind of obvious, but then the thing that I thought was kind of interesting was that they don't catch up at equal rates. So, for example, if you're going at 1.5 miles per minute and there are two cars behind you, one is traveling at 1.7 miles per minute and the other one is traveling at 2 miles per minute, then the one that's going at 2 miles per minute is going to catch up with you twice as fast as the one that's going at 1.7 miles per minute. And so this means that at any speed, you're not going to see an equal distribution of car speeds. And so I kind of formalized this into basically sort of quasi-density function, or like how things are related to each other. So this is what it looks like. And I said, okay, traveling at 1.5, this is kind of the density of the things you're going to see. And then if you're traveling at different speeds, this is kind of the density of the cars you're going to see at different points. And so that was it. I thought, okay, I have the density of what cars you hit. I have the loss when you hit a car. Now, what I did, instead of simply putting them together, I kind of went down a bit of a rabbit hole where I thought, okay, this is actually a probability density function. But if you do the math, the area under the curve doesn't equal 1. And for a probability density function, you have to have this being true. So what I did then is I kind of overcomplicated the question, and I got the expected loss is equal to this, which is basically my poor attempt of turning this into a probability density function multiplied by the loss when you get hit by a car. And then what I did is I basically just plugged this into an integration calculator and got the result, and it was kind of nonsense. It was like minus something. And so that's when I thought, okay, you're probably going off the wrong track. Then I realized that the PDF of this density function doesn't have to integrate to 1, and that in fact we can infer that cars traveling at different speeds actually get hit more often than others. And so it basically looks like this curve, and that's completely fine, instead of what I was insisting, which is that it has to be kind of a flat line up here. Correct equation, I should put that in quotation marks, it's actually wrong. So then I got this much more simpler form of the equation, and I thought that this was the correct loss. And so because this is, by the way, for here, this is the loss when you get hit, and this is the area under different sides of the curve. So up here, basically this component of the equation is this part. So this is all the values that can potentially overtake you. And then in this side of the equation, when you're below the threshold, this part of the equation is basically all the car's speeds above you, but that are also below the threshold. And that's how then I got the losses when you're under and over the threshold. And this is how I came up with this equation for the loss. And then, of course, quite simply, I split the, I just basically solved it. I put the derivative of the expected loss equal to 0. Bam, bam, bam. Use the Leibniz integration rule to get these equations, blah, 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 plopped into an integration calculator, and I got 1.226 bunch of digits. And then, okay, I've gotten this. I submitted my answer, no results. And then finally the answer came out, and I realized where I'd completely gone wrong. And where I'd gone wrong is that I simply misread the question. So what I was doing here with all this triangle nonsense and getting densities of what gets hit, this is not needed, because the way that cars spawn or cars appear on the track is not actually from a uniform distribution. It's actually just appearing uniformly over the highway, which basically leads you to a completely different solution that you can read on the website. And so that's basically how I got it wrong. It's just not reading the question and kind of doing my own thing with uniform distributions instead of assuming a uniform rate of cars appearing. So that's how I failed to solve the James Street puzzle. Thank you very much for watching.